Hi, everyone. Today we're going to be talking about a elaboration on the linear combination of unitaries strategy for building algorithms. And this particular approach that I'm going to be talking about is known as the quantum singular value transformation. The quantum singular value transformation in general is a method that's actually used to implement a function of a block encoded matrix in a direct way. Now, there's a lot of discussion about how this is done in the literature, and typically the way that it's presented in the literature is slightly different. There's a more qubit optimized way that's discussed, but it's less explicit about how you end up exactly constructing the circuit in order to do the polynomial transformations that we're going to be looking at on the block encoded matrices. So for that reason, I'm going to be showing you a simpler but less memory efficient technique based on linear combinations of unitaries. So let me just jump right over to my slides. Oh, and share my screen. Very good. Great. So the basic idea, as you recall from linear combinations of unitaries, is we had a couple of operations. The first one we had was an operation that I called prepare. Now, and just to be clear, what we were trying to do is we were trying to build A, which can be written as sum over J, alpha sub J, U sub J over here. Now, prep was defined to be an oracle that ends up loading in all those alpha sub J's that we need to define the expansion of the matrix A. And this is sum over J square root alpha sub J divided by normalization constant square root alpha, where alpha is defined to be equal to the sum over J alpha sub J. And also, without loss of generality, we assumed that alpha sub J is greater than or equal to 0. So that's the basic, that's the first operation. The next operation that we defined was the select operation. Now, select has the action that when you choose a particular value of J and a state psi, select will end up mapping J psi to J U sub J psi. Or another way of expressing this is that we can write select as sum over J, projector onto J, tensor U sub J. We can see that actually if we use this definition, the two operators, this operator for select down at the bottom has the same action as the one on top. So this is the select operation. Now, what we did is we introduced an operator L, and L was equal to the following circuit. It was equal to this situation. I guess the psi and the 0 just to guide the I here. This is prep dagger, prep select. And as I mentioned last time, this is a really familiar form, right? It looks like the Hadamard test. It looks like the swap test. It looks like a bunch of the stuff that we've already kind of covered to death at the moment. And so that is the operation L. Now, we showed last time that L block encodes the matrix A over alpha up here. And what we meant by block encoding is we meant that if we flag this top qubit over here, or top register, which here is 0, okay, so let's say I do this sum from 0 to m minus 1. This is going to be of size ceiling log base 2 of m, just to have enough qubits in order to be able to store all those values. But let's not worry about that. I'll call this value little m. And so this will be like flagged by 0 to the m, and this would be 0 to the m. And in particular, if we apply this state A over alpha on the initial state, which would be 0 psi, then if we measure these outcome bits to be 0, then we end up getting A over alpha psi divided by the length of A over alpha psi. Okay, cool. And another way of expressing this, if you recall, was that we can end up expressing A over alpha as a projector onto this block. And we can define the projector onto the block using Dirac notation with in the following way. This is 0 tensor identity, which selects that column. And then we have L and 0 tensor identity, which selects, I believe, the row. So the, but it could be the other way around, doesn't matter. So anyways, the matrix A over alpha is the block encoded up here by L in this particular fashion. Okay, fantastic. So now the next step is that we want to go on to is we want to go on to singular value transformation. Now, the singular value transformation, what we seek to do is we seek to start with a block encoding. That's A over alpha in this particular form. And what we would like to be able to do is we'd like to be able to block encode this matrix in an even larger matrix. And we'd like to be able to do this so that we can get enough flexibility to end up implementing a block encoding of the following form. So we're going to build an even larger space so that it's not just A over alpha that's block encoded, but actually a function, an arbitrary function of A over alpha. Now, what functions are the kind that we can do? The kind that we're going to discuss how to do is we can implement f of x for any polynomial function f. Okay, so that's the basic idea. Now, why would we want to be able to do this? Well, there's a bunch of different reasons. One reason is, for example, let's say what we wanted to do is I wanted to be able to perform the matrix inverse. So if I wanted to implement A inverse, but I only know block encoding for A, well, all I would have to do is build a polynomial of the form sum over j, a sub j, a to the j, equals f of A, such that the norm of f of A minus A inverse is smaller than some air target that we want. So this is how actually we're ultimately going to solve the quantum linear systems problem, is by doing such a transformation. But that is, okay, so that's the high level view of how we're going to be doing it. But let's get a little more specific about the way that we're going to do it. The way we're going to build this is actually just by using the same idea as we had before, except in order for us to be able to do this, what we're going to do is we're going to express all of this guy as a linear combination of unitaries. And you can see that we can fundamentally end up doing this because A itself is a sum of unitary matrices. It's alpha sub j, u sub j. So if I substitute this in, what we end up getting is, okay, let me change that to k, I guess. Then this is equal to sum over j, a sub j, times sum over k, alpha sub k, u sub k to the jth power. Now, if we expand this guy out, then we're going to get also a linear combination of unitaries. So you see that in principle, we can use the exact same formalism in order to be able to implement this. But actually, it's often going to be a pain to do that. The reason why is that the number of terms, if k goes from 0 to little m, or sorry, I guess big M minus 1, the number of terms that we end up having in this series is in order j equals 1 to like k or 0 actually, is going to be in the on the order of m to the capital K. So that blows up exponentially. And the exponential blow up means that, well, f of x is just not necessarily going to be practical to implement directly using the previous ways, because we would have to build a prepare and a select oracle in order to be able to program in this exponentially large number of terms. And that's just going to suck. So the way that we're going to get around this is we're going to basically kind of build up a more general circuit that is going to be able to do any arbitrary polynomial, and we'll analyze it the same way we did last time in order to show that the whole thing works. Well, in order to do it, there's one other little piece that we need, right? Our function, f of a, is equal to sum over j, a sub j, a to the j. Well, we need to feed these in. So I'm going to define this function called prepa. Okay, and what prepa is going to do is prepa is going to map 0 to the sum over j, square root a sub j divided by a constant root a times j, where a is equal to sum over j, a sub j. All right, wonderful. So the way that we're going to do this, and I'm going to assume here that for the particular polynomial that we're looking at, that a sub j is greater than or equal to 0. The case where it's negative can be easily handled by introducing phases in appropriate ways in different things. So it's not a big deal. And for the sake of simplicity, we're just going to look at this case. All right. So first thing that we end up doing is we basically are going to try to build a circuit that ends up looking like the following. Our circuit is going to consist of a series of different preparation circuits that will end up pairing the coefficients of this and also the coefficients of each of these different powers of j. So if we look at this expansion over here, we can see that when we expand this all out, we're going to get every possible mixture for any fixed value of j of the alpha coefficients and the u sub k coefficients. But each of the distinct powers of j is going to be kind of wed to this a sub j that's multiplied through by everything. Okay, so that is how we're going to do it. We're going to create a series of registers off to the side, and each of these registers is going to have an ordinary prepare circuit. And each of these is storing the coefficients that we have. Now, the target state that we want to evolve is going in here. Everything else is 0 over here. And if we're going from j equals 0 to k, then the number of registers that I'm going to need here is going to be of size k. And each of these is going to contain m bits, which is equal to a ceiling of log base 2 of capital M. Okay, so the total number of qubits that we need is going to be that. Now, there's another thing that I'm going to end up assuming just for simplicity. That is actually just in the nature of this encoding of the prep A state. So the thing that we're going to assume is we're going to assume that prep A ends up preparing the values j over here in a unary encoding. So in particular, the type of unary encoding I'm using, and unary encodings are actually they're kind of like Roman numerals if you think about it. And the way that I'm going to be using a unary encoding is the following. let's take our decimal values here, and these are our unary values. So if we have 0, I'm going to represent that as 0 in unary. 1, I'm going to represent that as 1. 2, 3, 4. You get the idea. So the number of ones that we end up getting, or the Hamming weight of the string in this unary representation, is actually going to be equal to the decimal value. And the reason why we do that is because it's going to be a lot easier to end up controlling this on it. So in particular, the way that the summation is going to work is actually we're going to take the sum to be the unary version of j, which I'll denote like this. And so if we've got a sum from 0 to k, then the total number of qubits that we're going to need in order to deal with this representation is k. Okay, so that's the basic idea behind it. So ultimately, we're going to need like k times m plus 1 different qubits in order to be able to store this. Okay, so now that we've prepared this, we've built all the different superpositions that we're going to need for the AJs, which are the prep-as up here. So just like these guys. And then what we need is we need to get all the coefficients for each of the A's, and those are stored here. Now, we also are going to need to build in, for each power of j, the corresponding unitaries that are applied to psi. So just to make it clear, right? If this is, if we're looking at a to the j, right? This over here is going to correspond to like the first power. So this one over here, okay, let me just, I guess, be a little more specific. Imagine I had a plus b cubed. This is equal to, well, a plus b times a plus b times a plus b. So each of these registers over here corresponds to a different power. And what we're going to want to do in this series is we're going to want to check to see if for a particular value of the j term up here, which corresponds to a power of the polynomial, we need to check how many of these different groups we're going to need in the a sub j to phi. So this one is just going to be the first one. It's going to be this guy in the expansion. Next one we're going to take to be the second, which is this over here, and so on and so forth. Because of the nice feature of unary, if I take this one a bit up here to the least significant bit, we can apply the select operation, i.e. selectively apply A or B to the state psi by doing the following control logic. We will do a controlled version of the select circuit here. Now, what I've done is I've used a notation where I'm drawing a box to represent some of the inputs in here. So basically what this is saying is that the select operation is going to be taking as input this register to store the superpositions of the J's that it's selecting off of, and its target is going to be down here at psi. Then the second power, we want the second power to be triggered if we have a state 2 or a state 3 or a state 4. And so the way we're going to trigger that is by following the exact same pattern here. Okay. And then finally, continuing all the way down to the last case, which is going to look like this. Okay, now we have that particular state. And now, just like we did before with linear combination of unitaries, we needed to unprepare all of these different operations. So we'll put prep through a dagger. I guess this is going down here in a dagger, and this is prep dagger. This is prep dagger and prep dagger. And then we're going to define success over here to be the case where all of these are going to be measured as 0. Okay. So in particular, this seems like it's actually going to be a really unlikely event, because everything considered, if we count the number of qubits, we have k plus 1, k times m plus 1 qubits to represent everything. So having all of those all equal 0 seems like it's going to be exponentially small. But in fact, actually, we're going to see that in many cases, this is surprisingly likely. So let's go on and actually go through the analysis for this circuit. So the circuit, let me just copy and paste this guy. Just so that I've got a visual aid while I'm going through it. Okay. So we've got this particular circuit. And what we want to do is we want to now first go through all of the, well, I guess actually there's a couple of ways we could do this. We want to show that this creates a block encoding, right? So we want to show that this is going to create f of a over alpha divided by a up here. Okay, so we're going to write that block encoding as the following way. We're going to have 0 tensor basically everything except psi, tensor identity acting on this circuit. I'm going to call this whole circuit L sub f. So this is going to be L sub f, and we're going to want to do the same over here. Okay, and all these two projectors are doing is they're just allowing us to focus our attention only on this block and not have to algebraically go through a lot of manipulations to deal with these other subspaces that we're ultimately not going to care about. So this is the action of L sub f. And so L sub f, again, is of the form. This is going to be 0 up here, tensor 0, tensor 0, tensor I, all multiplied by prep a dagger, tensor prep, tensor prep, times the controlled selects. So the way going to write the different controlled selects is I'm going to write it as a product over the I'm going to write this as okay, I'll just be a little implicit about this. I'll write this as the product over the controlled select sub j. And then we're going to have prep a dagger tensor prep tensor prep over here, all acting on the state 0 tensor 0 tensor 0 tensor identity. Okay, so that's our state. Now we're going to go through and we're going to do basically the same thing that we did last time. This is going to be equal to the sum from this is going to be something that we can write as the sum over two indices, I'll call them P and P prime, square root of AP prime from the prep A acting left and the prep A here. Oh, sorry, there shouldn't be a dagger there. The prep A acting right. That will give us the square root AP prime, all divided by A. Then what we are going to end up getting, or actually, let's express it as the following. Or no, actually, this is okay. Yeah. And so we'll have that. And then we're going to have the sum over all of the individual values in here, which we can end up writing as sum over Q1 through Q capital K of square root alpha Q1 through alpha QK times the square root of alpha Q1 prime. I guess I'm going to need the sum over Q prime as well through alpha QK prime. Again, these are from these sequences acting to the left and to the right. Oh, and these should be daggered. Okay, so we've got that. And now we've worked out all the coefficients. We just need to be able to apply the states. Now, the states are going to be of the form P prime sub U. And this is just, again, the unary encoding of the state prepa acting left, because we defined prepa to always give the unary encoding rather than a decimal encoding. And that was done so that the control structure here becomes much simpler than it would be if we ended up using binary. I should mention that obviously we're wasting memory a little bit by doing this, but the memory we waste is more than made up for by the simplicity of it, especially because of the fact that most of the time the value of K that we're going to need is going to be less than 10. So we'll need 10 extra qubits for this. And so the savings by going to binary actually aren't that significant. But in any case, this is psi p u, and then we've got to deal with the values for all of the quantum states from the action of the ordinary preps. And these are just going to be Q1 prime through QK prime. Now, then in the middle, we've got the controlled J operations that we end up having here, which are all of the form C select. We'll deal with those in a sec. And then we have the remaining states over here, which are just PU. I think there should be an identity here, and PU going all the way down, Q1 tensor Q sub K tensor identity. Okay, cool. So that's our resulting state. Now there's some simplifications that we can end up making pretty much immediately from this. We see that because of the fact that the select operation doesn't end up manipulating the Qs or the Ps in this case, because those are the controls that choose what unitary is applied to the final subspace, we see that the inner products are going to be 0 on the right-hand side unless P prime equals P, Q1 prime equals Q1, and all the way down. So this ends up giving us that this is equal to sum over P, AP over A, sum over Q prime, or Q1 through QK of alpha Q1 through alpha QK. Oh, did I remember to divide through by the normalization constant of this? I think I might have missed that. So the normalization constant in the denominator is going to be, I believe it will be alpha to the L over here. Okay, or alpha to the K, sorry. Okay, so we've got each of these guys divided through by alpha to the K times the an operation that will look like P Q1 QK product over J select sub J times identity, all multiplied on the right by P Q1 through QK tensor identity. All right, cool. So then now the next thing that we're going to need to do is actually just do those select operations. So select J is only going to fire if the jth bit of P is 1. So we can end up seeing that this will end up giving us something that is equal to sum over P, A sub P over A, sum over Q1 through QK, alpha Q1 through alpha QK, divided by alpha to the kth power. Now, this is just going to contract all the way down. And the only thing that's going to kick around are the unitaries produced by select J, where select J, again, is defined, or the controlled select J is defined to be of the form. It is defined to be of a form J tensor select plus identity minus J tensor identity. So sorry, I think I might have actually, when we were discussing this earlier for a cute way of expressing the select operation earlier, I might have actually failed to mention this. Oh man, is it doing it again? I hope not. Yeah, it's doing it again. Fantastic. I have no idea why it's doing it. Okay. But moral of the story is, sorry about that. I forgot to input the identity minus JJ tensor identity, meaning that if the input isn't J, then don't do anything. So key point is when we expand this out, what we end up getting is the following. Okay, what we end up getting is we're just going to end up getting the product from over the distinct values that we have here of U acting on the binary or the unary representation of the value of P. Well, I guess actually, yeah, the unary representation of the value of P's kth bit. Yeah, this is, I think, a better way of looking at it. Going down to the unary representation of P's first bit, acting on our particular state. And this is all divided by alpha to the k. Wonderful. So it helps to go through some case analysis in order to be able to understand how this linear combination of unitaries operator ends up working. So let's first consider the value where p equals 0. So in that case, if p is equal to 0, then that particular term is going to be a0 over a. Now, we still have the sum over q's here to qk. Alpha q1 through alpha qk divided by alpha to the k. However, in this case, p is equal to 0, which in unary will be a binary string that's all zeros. Therefore, each of these bit values is 0, meaning that, or in other words, the control sequence that causes those unitaries to fire never shows up here. So none of those unitaries fire. And all we're left with is actually just the identity operation. So we can simplify this, however. This is equal to a0 over a, sum over q, alpha sub q to the kth power, because each of these sums is completely independent, also divided through by alpha to the k times identity. This is, of course, equal to a naught over a, because the sum over q, alpha sub q, is defined to be equal to alpha. This is actually just equal to alpha to the k divided by alpha to the k. These two cancel, which just gives us a0 over a. There you have it. So that's how we end up doing this with the first term. Now, if we go to p equals 1, on the other hand, then what we would have is we would have a1 over a, sum from q1 through qk, alpha q1 through alpha qk divided by alpha to the k. Now, all of these different products that we end up seeing, out of all of them, there's only one that actually ends up surviving, and that is going to be u p1, which is just 1. So this is u over here. So all of these are basically going to end up contracting with, oh, sorry, I forgot to index them. This is like uq1 through uqk, or uqk through uq1, right? I forgot the unitaries have indices. Sorry about that. So now we have, this will be uq1 here. Now we can apply the exact same thing for all the indices except the first one. So this is going to be sum over q1, uq1, because these are just numbers, they commute with any matrix. So we can express this as the sum from over q2 through qk of alpha q1 through alpha qk divided by alpha to the kth power. And we see that this now will end up giving us a1 over a alpha to the k, alpha to the k minus 1, sum over q1, alpha q1 uq1. All but one power will die, leaving us with that. Okay, so in general, going through the exact same pattern, you can see what will happen going all the way up to k. Well, as we end up increasing the index of p to k, we'll have more and more of these u terms and less cancellation on the denominator. The pattern, once you go through, it's easy to verify for yourself that this ends up yielding sum over P, A sub P over A. What's the best way to end up writing this? Yeah, so the best way of writing this will be that this is the sum of AP over A, sum over Q, alpha Q over alpha UQ to the Pth power. And so now, noting all of that, we see that this summand inside the power is actually just equal to, by definition, since A is equal to sum over Q, alpha Q, UQ, this is just equal to A over alpha, which is equal to the sum over P, A sub P divided by A over alpha to the Pth power. Now, we've defined f of A over alpha is equal to sum over P, A sub P, A over alpha to the P. And therefore, this is also just 1 over A, f of A over alpha. So we can see here that we can implement any polynomial transformation that we feel like by using this particular idea. And so this is something that is really important. I strongly recommend that all of you spend time to try to go through this derivation yourself. If the way that I ended up doing it without trying to introduce a psi was confusing, I'd recommend going through the whole derivation of the circuit, which ended up looking like, prep, and then of course the nested controlled selects on the state. Actually, I guess, yeah, going all the way down to that box, and then prep dagger, prep dagger, and prep dagger. Okay, so I recommend going through this particular circuit, even if you don't do it in a basis, in the input independent way that I tried to do it here. And you just use these input states and go through. When you go through this using the exact same reasoning we have here, you'll end up seeing it. And if you can go through and get this right, then you'll fully understand how linear combination of unitaries works. And I think that there's no real way that you can get this without doing it yourself. So I strongly recommend take the time, do this. It'll really help the rest of what we're going to do, which builds upon this, make a lot more sense. But so thank you very much. Hope you all enjoyed this and weren't fully mystified by it. But the key point, again, just if you get nothing more out of this, then quantum singular value transformation gives you a way of implementing the power of a block encoded matrix. And it's called a singular value transformation, at least in this case where the matrices that we're transforming are diagonal, not diagonal, are normal matrices, because of the fact that all normal matrices can be diagonalized. And so if we raise one of these matrices to a particular power, right, then, or I guess actually more appropriately, if we consider a function of this, then the way that the function is defined is it's defined to be a function of the diagonal matrix, with U transpose happening here. And so that in effect is saying, because this diagonal matrix is the eigenvalues that we have for the for the matrix in question, this transformation function that we're considering on the block encoded matrix can be viewed as actually just a transformation on the eigenvalues of the matrix, keeping the eigenvectors intact. So that's what earns it the name singular value transformation, because singular values are a generalization of eigenvalues. And so that's the aim, and we're going to be using it a ton to do quantum simulation, to do inverses of matrices, and actually more general ideas like fixed point amplitude amplification. So I hope you've all enjoyed this, and yeah, see you around next time.